Hello, everyone, and welcome to the 28th Surface Ventures webinar. So before we get started, could I please ask you to write where you're joining from in the chat box? We just want to make sure we're coming through loud and clear and that you can hear me before we begin. Okay. I see we've got quite a lot of registrants loaded in already. Oh, excellent. We've got people from the USA, San Antonio, Canada, Munich. Fantastic. Great. Glad to have you all with us. So my name is Dr. Sam McMaster. I'm the event manager here at Surface Ventures, and I will be your host for today's session. So before we begin, I'd just like to let you know a little bit about Surface Ventures. If this is your first time, we are a non-for-profit organization, and our mission is to provide world-class surface engineering education for academia and industry. So every month, we bring you a sector-leading speaker to tackle the current challenges and future trends in surface engineering. And alongside this, we also have surface engineering workshops and live equipment demonstrations. So fantastic. Great. Thanks all of you for typing in the chat. So today, it will be my great pleasure to introduce Professor Suman Shrestha of Keronite International, which is now a part of Curtiss-Wright. So Suman is VP of Applications Engineering at Keronite Limited, with over 20 years experience on plasma electrolytic oxidation. Prior to Keronite, Suman extensively worked on a wide range of thermal and cold spray coating systems at TWI. He's a visiting professor at the University of Leeds, Industrial Advisory Board member for the Universities of Leeds and Manchester Metropolitan University, and is also on the board of Surface Engineering and Tribology Materials, Surfaces and Interfaces, both of those being journals. He is a chartered engineer, chartered scientist, fellow of both the IOM3 and of the IMEC-E. Suman was twice the recipient of Nepal's highest educational decoration, the Order of Mahendra Vidyabhushan Medal from His late Majesty King Birendra. So in terms of agenda, we will begin with our speaker's presentation quite soon. We'll have a short video and a presentation from Gregor Patzer of Optimal Instruments, who are the partner for this webinar, before the Q&A session at the end of the event. A quick note on questions, so please type these into the chat. So I will mark those as questions, and we will address those at the end. So we're planning to go around 60 minutes today, but depending on number of questions, this may change. Additionally, we will be offering attendance certificates for everyone who has attended live today. The link to that will be shared later in the event. And before we begin, just want to give you a quick reminder about our website, surfaceventures.org. It features videos from our previous talks, information regarding upcoming webinars, and information about the Surface Ventures team. So before we begin, I'd just like to launch a quick poll question, and there will be a few more of these just to find out a little bit more about you. So this one is, what is your current job/position? Okay, so with that, let's welcome Suman to the stage. So we'll just do that, and we will be setting up a screen share with Suman. So if you just bear with us just for a minute or two whilst we get that set up. Okay, excellent. It seems we have a very good mix of students, researchers, some managers, etc. Welcome, Suman. Great to have you with us.
Thank you. Thank you, Sam.
Okay, so Sean, let's get the screen share set up, and then I'll leave stage and let you get on with your presentation.
Okay.
Okay. Just wait a moment for this to load up, everyone. Okay, is that we're just waiting for it to load, Suman?
Yeah, that's fine.
Okay. So can't see anything on screen just yet.
Do I need to share the screen there?
Yes, please. Sorry.
Sorry.
Yes. do. No, it's okay. It's okay. Okay.
Is that the right one?
Excellent. So I can see the slides. Wonderful. So one quick thing before you begin. So you'll see that event.demio is sharing your screen. Could you just please click the hide button on that? Just because that might obscure some of the slide elements there.
Are you asking me, Sam?
Yes, please. So just there's that little pop-up that says Demio is sharing your screen just in front of your slides. So if you could just click the hide button on that, please.
Event, no, stop sharing, hide. Oh, hide, this one.
Hide, please.
Okay.
Yes.
It's done.
Okay, perfect. Thank you very much. I will now leave stage and I'll let you start your presentation.
Okay, shall I start?
Please.
Thanks, Sam. And thank you all for having me today. My name is Suman Shrestha, and today's talk is about a novel coating technology for light metals. The process is called plasma electrolytic oxidation, or in short, PEO. This is an advanced surface technology invented, developed, and matured for industrial applications over the last 20 years, with specific focus on light metals such as aluminum, magnesium, and titanium. This is also a breakthrough technology that would enable us replace heavier steels on critical applications and help towards manufacturing cost reductions, reductions in emissions, and materials and environmental sustainability. Let me give a bit background about the company. Caronite is the company behind this technology, and we specialize in the development and the commercial application of an environmentally friendly advanced surface technology throughout the world. The global headquarters is in the UK, and also we have got the US headquarters in Indianapolis. The patented PEO process converts the metal surface to a dense and durable oxide ceramic layer of unparalleled characteristics that enables these light metals to be deployed in highly demanding and aggressive environments. Now, from November last year, we are part of Curtiss-Wright. Just to give you a bit background about Curtiss-Wright as a corporation. Curtiss-Wright has an incredible history, proud history. Curtiss-Wright was formed through the merging of 12 Wright and Curtiss companies nearly a century ago. Just sometime I'd love to tell about history, about, let me say a few words about Curtiss-Wright. For those who haven't heard about Curtiss-Wright, Glenn Curtiss, he was the father of the US aviation industry. And I'm sure many of us may have heard about Wright brothers when we were younger in the schools, and they were credited with inventing, developing, flying first in the world a motorized aircraft. There you go. It's a very proud history. And today, Curtiss-Wright is a global technology corporation offering products, solutions, and services in a diversified industrial market from aerospace to oil and gas to power and generation and energy sector, defense and automotive and medical electronics. And Curtiss-Wright has its own surface technology division that offers solutions in the materials and surface technologies. It has got over 75 business units across the world, as you can see, with lots of dots in North America, in Europe, and a few in Asia too. And now we'll be joining, Caroline will be joining to add 2 more dots there, one in North America, in Indianapolis, and another in the UK. When we talk about light metals, the first thing comes into my mind is the aluminum. It is probably the most widely used metals, light metals. Aluminum production is more than all non-ferrous metals combined and considered the second king of metal after steel. Aluminum is considered as a developed metal rather than a discovered metal over a century ago. And today its production has grown exponentially from zero about 1900 to now over 75 million tons a year, because aluminium is so attractive in diversified applications. You can see on these pictures in aerospace and ships and drones and satellites, on textile, automotive, and in everyday products like laptops and phones and cooking frying pans, etc., etc. So all of us may have or have at some point touched aluminum as a material. So it has got an extensive applications portfolio. So why light metals then? First of all, as it says, it's very attractive because it's quite lightweight. Imagine that you have to transport lightweight components, parts, anything from one part of the globe to another. You save fuel, you minimize emissions, right? And if you imagine, if you have to lift off against the gravity, 1 kilogram weight to the low Earth orbit, you save $50,000 per kilogram. That's a massive saving, right? Some of the key strength of light metal is substantially lighter. For example, aluminum in our case is 2/3 the weight of steel. It has got very good mechanical and physical properties. And most importantly, it can be manufactured in varieties of ways, from extrusion to rolling, cast, injection molding, and advanced joining technology, and now also lots in powder metallurgy, where you have got extremely minimal wastes. And most importantly, it is highly recycled material as well. But it does come with weaknesses. Of course, the poor corrosion and poor wear is the main drawback of these light metals. It's thermodynamically reactive and is soft as well. And hence, we have got a big challenge there. We are continuously searching for new surface technologies that can meet new environmental legislations and also that can offer multifunctional properties to enable us these light metals to be deployed in highly aggressive environments. Sorry. Why next one. So why the PEO is a unique surface technology? Before we talk about PEO as a unique surface technology, I would like to do a couple of minutes on these slides. We have got these 3 different technologies here. The left one is your thermal spray, very well established during 90s, in particular the HVOF. Plasma spray was from 1950s, very well-established technology and widely used in industry. It's a very versatile equipment, technology. It can deposit material of different kinds, from metals to ceramics to ceramics, on different types of substrate. And how it works, I'm sure many of you have already know about this technology. You have got these particles, solid particles, usually in the powder form, 5 to 50 micron powder particles. You heat those to bring those to molten or semi-molten state with a heat source, either using plasma or the oxy-fuel combustion. And you propel with very high velocity to deposit onto a pre-prepared substrate. And we already have some great blasting done for mechanical king. The challenge with the thermal spray, despite of its having very high attractiveness and very versatility, is that sometimes it becomes very awkward on light metals, primarily because of the CTE mismatch, the variations of the expansion coefficient between, let's say, aluminium and the incoming particles, very hot particles, that leads to the coating poor adhesion and flaking, etc., etc. On the middle one, you have got, again, very well established technology, nearly century, hard anodizing, used on many, many applications, but for moderate to non-severe applications. How is the process done? As it is said, anodizing, the part is made an anode in an electrolytic cell, and a DC voltage is applied. And you can see the hard anodizing is done primarily in acid-based strong solutions. And that's one of the key drawbacks, is because it will have some environmental effect. So you move on to this PEO as a technology, which is around 2000 commercialized, as you can see. The main fundamental difference between the PEO and the anodizing, for those who are not familiar, is that both are electrolytic. There are similarities. Unlike the thermal spray here, which is a solid state deposition and additive process, this is probably a subtractive process. You dissolve the surface and convert that into aluminum oxide, primarily amorphous alumina. Here on the PEO process, what you do is you apply extremely high voltages in excess of 500 up to 1000 volts. And by applying the high voltages and high electrical field, you generate plasma on the surface. That is the essence, the fundamental of the PEO. You generate plasma on the surface, and hence plasma electrolytic oxidation, or PEO. The other benefit of the PEO is you often use environmentally safe electrolyte, very low concentration, less than 5% solid content. It's typical of a dishwasher liquid that could be disposed of to the normal sewage systems. So this makes the technology unique, and also because it being an electrolytic process, you can coat extremely complex shape, which is poor line of sight. So let me mention a few things about, as a principle, as a PEO, how it works. Often I love to present this picture when I tell about the PEO. It is how a humble clay converts into ceramic pottery, because the clay comes into contact with fire. And as from the Greek word, the keramikos is ceramic, it means burn stuff. And that's why by burning that stuff, you convert into a ceramic. And exactly the same approach we're using in this process. On the right-hand side, you see the vertical axis is the voltage in the process, and the horizontal axis is the processing time. This is a one side of the bipolar process, a positive cycle of the PEO process. You have got this aluminum at the bottom, and you start to have electrochemical reactions, right, during the PEO process at lower voltages. Just like in hard anodizing here, you start to dissolve the surface, create aluminum ions, and react with oxygen ions to convert amorphous aluminum oxide. Once you increase the voltage further, around 200 volts, you start to see luminescence. And that's why you tend to have a stable amorphous oxide layer there. And once you exceed that voltage, you're creating a high voltage and high electrical field. You are creating plasma discharge on the surface because you're exceeding the breakdown strength of these amorphous layers. And that's what the fundamental change is when that comes into contact with fire, just like these potteries. This amorphous layer of hard anodized or amorphous layers formed during the PEO process starts to convert into a hardly dense ceramic crystalline inorganic oxide. Usually here in this case is aluminum oxide or alpha alumina or corundum, very, very hard. This video was taken by Cambridge University student. You can see what happens during those plasmic discharging events. Millions of those discharging events are hitting on the surface, and you're really melting those aluminum oxide, refusing, recrystallizing, and coalescing together to make an extremely durable ceramic oxide layer. Coating design is one of the interesting things about the PEO technology. As mentioned before, thermal spray, you can put down a variety of coatings on a variety of substrates. Of course, the PEO technology has got some limitations. It is only applicable to light metals. But the interesting thing here is you can put different things input, like electrolyte formulations. You can change the ionic constituents. You can change the electrical parameters, like the waveform, the duty cycle, pulse shape, etc., etc. And by doing so, you can have variable outputs. For example, on the left-hand side, you have got a highly fused alumina surface, very dense. You can see the bottom is the cross-section of the same, quite thick, about 100 micron thick coating, extremely well adhered. We call it atomically bonded coating to the substrate, very uniform, right? On the middle picture, this one here, you can see a highly porous coating architecture. So you are preparing the porous scaffolds for various reasons. It could be to deposit a secondary layer, such as paints or powder coats you can apply on top of it, or this could be with deep pore architecture, like an optical light trap for space missions, for cameras, maybe for optical housing, where it gives a very, very low optical reflectance. On the right-hand side, you can also create like aluminum oxide or magnesium oxide spinel type coating, for example, where you can also trap porosities with air trapped, to offer them a properties which has got very, very low thermal conductivity and low specific heat capacity, for example, for applications like thermal barrier coating or piston applications. Microstructure is quite key. If you see, this is on the top is the hard anodized coating, and the bottom is your PEO ceramic coating on the same alloy. And you can see the corners in particular, this hard anodized coating often suffered is we call as a truncated V cracks that results in massive fatigue drop, up to 50% fatigue drop. This is the cross section. You can see those truncated V cracks extend down to the substrate, of course, making it vulnerable to corrosion for fatigue drop, etc. On the bottom picture here is the same region with the PEO. You don't see those wide opening defects or cracks. It's very uniformly covered as well. And you see the cross sections here, very uniform coverage of the cross section. Flexibility is another interesting characteristic of the PEO technology because of those plasmic discharge events, millions of those happening on the surface. You have got this microscopic pores, the shrinkage cracks, etc., etc. That allows you to make the coating very flexible. And one of the Cambridge University PhD guys measured the Young's modulus of these coatings and found to be an order of magnitude less than the monolithic ceramic. That allows the coatings to be flex and make it very strain tolerant. Adhesion is another interesting features. I would like to show you 3 pictures here. On the very left is the hard anodized coating, very good interface, good adhesion. This is a thermal spray, the plasma sprayed alumina, with mechanical king primarily. You can see those from grid blasting, porous coating. This is the PEO alumina here, very dense, very well adhered to the interface. And if you see this plot here is the ASTM 6333 pull adhesion test. The adhesion of the PEO coatings were in excess of 80 megapascal, quite a lot higher than a plasma spray alumina. And this is here, the dark gray, the columns are for a PEO coated thin layer, typically for 3 to 4 microns to use as a pretreatment. And that's from the lab shear test, okay? If you see the adhesion values are very similar to chromic acid anodizing. So does it mean that we can replace chromic acid anodizing as a pretreatment? Possibly, yes. So we can. And there's a lots of already been used. And when we use this PEO as a pretreatment thin layer and apply subsequent secondary layer, for example, a paint or a powder coat, your critical failure to load the adhesion becomes extremely, extremely high. It's very, very resistant to scratch. Sliding and abrasive wear is another interesting factor here. You can see because these coatings have about 1,200 to 2,000 vickers hardness, which is a lot more than even hardened tool steel, which is about 800 vickers, and you have got hard anodized, which is about 400 vickers. This literally has about 4 times, 5 times harder than hard anodized coating, and significantly harder than hardened tool steel as well. And that offers an incredible wear resistance to the PEO coating. On the right-hand side is the abrasive wear resistance. You can see again, this coated PEO coated have a much less volumetric wear compared to even anodized steel. Corrosion is another interesting factor. As I said before, those truncated V cracks on the hard anodized coating results in the premature corrosion from the edges, for example. It could impact on fatigue and even worse in corrosion fatigue. The PEO coating doesn't tend to show those issues. On the bottom picture we have got here is a powder coated aluminum substrate. On the left one, you have got the chromic acid anodizing treatment first. On the right-hand side here, you have got a thin layer of PEO. So what has been done here is the powder coat was deliberately damaged, scratched, and exposed for 12 months of exposure to salt spray solution. So what you see here on the left-hand side is typical, we call as the corrosion creep. So the coating is migrating underneath the paint, resulting in blistering effect, and it is deep under the paint happening there. On the right-hand side, as you would expect, because the coating was damaged down to the bare substrate, you will see those corrosion happening here, but it is not migrating further because it stopped right there because of a very well adhered ceramic layer there. And of course, bear in mind that alumina is electrochemically neutral, so it doesn't accelerate galvanic corrosion or sort of like that. And having those excellent bond with the substrate and the excellent bond with the top coat or the subsequent layers, it gives you a very good corrosion protection even when it's damaged. Now, let's talk about some applications. We recently have big success in, especially on space missions. Caronite has flown to dozens of missions, including environmental mapping, Hayabusa, Euclid, meteorological operations satellites, Sentinel satellites, etc. Let me show you, first of all, one of the benefits of PEO is being able to coat. I call this a selective coating. You can see those, right? You can mask majority of the part is a thin sheet of TiO6 about 0.5 millimeter thick, and you just need to coat these windows black here for low optical reflectance. And this ability to give you to coat even those very selectively. On this middle one, I call it as the selective masking, because you are coating all the loads of these deep pockets and thin ribs, but also the need to mask these shiny areas are for masking for electrical grounding purposes. So the electrolytic process gives you all this ability to selectively either mask or selectively coat. On this top one picture, you can see here the specular reflectance. The PEO coating, the Caronite coating has got, in fact, very similar to the competing coating, or even better performance in a wide range of wavelengths. And other coatings are primarily paint-based systems, which are not good for a number of space missions. When we talk about the PEO coating in general, it is interesting to understand this. What it gives is the low optical reflectance and a very, very stable thermal control parameters we call as the alpha and epsilon values. One is the solar absorptance that controls the heat absorbed by the external spacecraft surfaces. And the next one is the infrared emissivity that controls the heat radiated to space. And both two parameters are called passive control mechanism. And these protect the equipment, the highly sensitive instruments on board the space missions. So why Caronite then? Because A, it is fully inorganic. It has got very, very low outgassing compared to the paint-based systems, right? It has got very consistent and stable properties. In fact, several PEO coatings have been tested on even on the International Space Station's Columbus platform over 18 months with absolutely no change in alpha epsilon values from the beginning of life to the end of life. And other properties, of course, it is highly thermally stable. It can withstand thermal shocks that you'd normally experience on space missions. And of course, it also gives you highly cold welding and corrosion resistant material. Another aspect of the space is the cold welding. Very often heard about. People often ask what is cold welding. Unlike arc welding and TIG and MIG welding, it is the welding process. It's the welding of two components coming in contact in a cold environment, right? On the left-hand side, you see a Galileo spacecraft high-gain antenna. Failed during deployment is because of the cold welding phenomenon occurred by fretting. And what is fretting? Is the process that occurs at the contact area between two materials under load as subject to relative motion by vibrations. So what happened here is the vibration during ground transport and launch resulted in destruction of the protection layers and hold down points by fretting, and subsequently the contacts welded. On the bottom one is a satellite mechanism, an anchor. It has got a repetitive motion and repetitive cyclic contact impact loading when this part moves electromagnetically from left to right. And what happens is the protective layers at those contact joints are damaged because the coating wasn't good enough or strong enough, and eventually it welds, leading to failure. It doesn't separate. So that's another problem. This picture here is showing again the two between the hard anodized and on the right. This is the top one here. You can see my mouse here is the Caronite PEO. After impact testing, there's no destruction of the surface. All this you can see is a steel ball transfer, steel material transfer to the Caronite surface. On the bottom one here is the hard anodized coating is completely damaged. After extensive tests on these parts, one of the successful story was the Caronite coating was sent to the James Webb Space Telescope on board the near-infrared spectrometer built by Airbus, which is one of the critical instruments of the James Webb Space Telescope. Tribology and friction is another interesting area. As I discussed before, you have got the PEO coating, and all these pores they act as a reservoir for either oil or solid lubricants, for example. And what is this? This is the picture of a ring that was coated with kaolinite composite structure, and that was successfully used to date on the world's largest space observatory in Gran Canaria. And this was the data from them is the friction coefficient of the kaolinite composite coating at different pressures. As you can see, very, very low friction coefficient as well. And today, similar PEO coating is already being used in various applications, including the Boeing 737 aircrafts. Let's talk a little bit about applications now. Is why I think we are very much involved more recently on these applications, the brake disc, and there's incentive for us because it's a volume market, and also we can make a difference to the environment. I'm sure most of us are very much aware of the brake disc technology, and mostly to date, grey cast iron is used. A very big grey cast iron for a mid-sized car weighs about 40 kilograms in total. It's about 9 to 10 kilograms per brake disc, right? And if we can reduce 20 kilograms, say by using aluminium disc weight, that could save 0.1 liter fuel saving per 100 kilogram, 100 kilometer of travel, and that means a corresponding reduction in CO2 emissions. It's not that people haven't thought about light materials. Yes, they have come up with aluminum MMC and CFRC as well, but they are extremely expensive and becomes unviable option outside of the high performance car and motor racing markets. So we thought, okay, let's try give a go on brake disc of aluminium made of. If we can save 20 kilograms, it can give considerable fuel savings, and also it can reduce unsprung mass, which is good for acceleration, deceleration, and also less damage to the road surfaces. When you say unsprung mass, is anything below the suspension, we call it the unsprung mass. Just to give you a little bit of background on this non-exhaust emissions, I'm literally learning over the last 5-6 years about this. People are very much not aware of these problems. And what I would like to show here is road transport particulate emissions or particulate matters, typically of known as 2.5 and PM10. They are submicron size. They pass through the lungs, go to the lungs, and create a lot of problem for human organs. And there's a good report done by COMIAB, the Committee of the Medical Effects of Air Pollution, on this subject. So this equation, what I'm showing here, this one here in particular, is that road transport PM is made of exhaust emissions and non-exhaust emissions, right? The exhaust emissions is everything that comes up the tailpipe, and the non-exhaust emissions is a combination of brake wear, tire wear, and road abrasion wear. And in fact, what it says here, the COMIAB report, is NEE particles from the UK road traffic have a greater public health impact than the exhaust particles. And they have reported about 29,000 estimated deaths across the country alone. And so it's very important that we can tackle these particle emissions, either from brake, from tire, or for road abrasion. This slide shows you the two plots here. What it shows here is on the left is a PM10, and on the right is a PM2.5. It shows here this yellow part is the PM emissions from the exhaust tailpipe. I think this would have tackled very well over the last 20 plus years. I think we have done very well despite the diesel scandals, especially the PM emissions. We managed to filter it through the exhaust gas recirculation systems or using DPF filters, diesel particle filters, etc., etc. So, but what we haven't been able to manage or tackle is the non-exhaust emissions here. It is slowly increasing, and if you see the projected numbers by 2030 is even growing more and more. So we thought, okay, let's give it a shot. And we put a nice proposal to the UK government, and Innovate UK funded this project. And what we did here is we tested an aluminium brake disc, a full size for a mid-size high-performance car. We tested this with PEO coating, and we measured friction coefficient and compared with the existing technology, which is the grey cast iron brake disc. And to industry standard. The test was done to SA J2522, As you can see, there's a lot of tests going on here, from harsh braking to a lot of snubs over these 8 sections of hundreds of stop numbers, sort of, if you like. And what this particular graph is showing here, the red here is the vented typical conventional gray cast iron, and the green one here is the ceramic PEO coated aluminium. In fact, the coated disc shows even better and less scatter, and very similar to friction coefficient of the existing material, and which gives us a lot of confidence for use of this material in such applications. Now, let's have a look on the non-exhaust emissions. And we have been doing for this test for a number of years. Leeds University has got an extensive facility and state-of-the-art facility in measuring those brake disc particular emissions. And this particular data was donated by our student, Fabian Lima, who's in the last year of his PhD. As you can see, the gray cast iron, the total mass loss from the gray cast iron system is over here, and the PEO coated is about 82% reduction in the mass loss. If you see on the right-hand side of this plot, the columns, the non-exhaust emissions, especially the PM10 emissions, again, PEO coated tends to show 78% decrease in PM emissions, and that is an incredibly encouraging data. Another interesting application is the electrical insulations. There's especially, as you can see on this one, this is the aluminum heat sink. Usually you have got this epoxy infused fiberglass to achieve high breakdown strength. The problem here is the lower conductivity, very low conductivity and a moderate breakdown voltage. If you see these epoxy fused fiberglass gives about 1,000 volts for 50 microns, right? If you have the same coating thickness with the PEO, you can achieve up to 2,000 to 2,500 volts per 50 microns, and also a much better thermal conductivity. It's like 5 to 10 watts per meter per Kelvin. But if you want to achieve higher breakdown strength, you can seal those PEO coatings with secondary sealers, for example, up to 40 to 50 microns, and achieve 5 to 10 kV breakdown strength, and while still having substantially higher thermal conductivity values than this epoxy-infused fiberglasses. Another interesting area is the aluminum tool. It is the low-energy aluminum tool heating technology, also funded by the UK government, the Technology Strategy Board. And here is the aim is to form complex lightweight component, lighter than metals, using this thermoplastic fabric. So what you need to have is a rapid temperature cycling is required, and hence aluminum is a fantastic material. So what we did there is we coated with an electrically insulative coating, a thin layer that could dissipate heat fairly quickly during high cyclic loading and fast cycling. Another one is the tribological applications. You can think about replacing steels, for example, now with this hard coating, whether it is clutches, gears, valve train components, and the semiconductor in particular. We are very, very active in semiconductor areas. Usually the semiconductor chambers, the cleaning chambers, the manufacturing chambers require chemical and plasma erosion, resistance against aggressive reactive gases. And they are highly complex parts. You cannot do thermal spray. Hard anodized coating doesn't offer enough protection, and hence we have got this new material, new coating. Another interesting area is the implants, the microsurgical instruments. This is an example of a dental implant. You can coat with a PEO coating and create this very poor architecture. And these coatings are TiO2, biologically inert and compatible for osseointegration. And also the pores we talked about in previous slides helps us to use them as a container for medicine, for example, antibiotics for faster healing. And also there's a lot of interest in robotic instruments, for example, for minimally invasive surgery, because these parts, those robotic surgical parts, are extremely small. You cannot coat them with thermal spray. They are so tiny, about a few millimeters in length, a couple of millimeters in width. They're very, very small. And the PEO as a technology gives an excellent opportunity to coat extremely small parts. Now, let's talk about some unique strong points rather than selling point. This is the USPs for me, is the unique strong points. The ability to coat highly complex shapes. On this left-hand side, this part is a threaded component. And let me show you, maybe, I don't know whether you can see in the video, this is externally coated and internally coated and the threaded as well. You can, Sam, can you see this? I don't know whether when I'm showing this, can you see that? Okay, I don't hear you, but okay. So this is what you can do with this.
Sorry, just here.
Okay.
Yes, we could see
Okay,
that. Okay.
all right, okay. And for example, with poor line of sight parts like this one, it's very difficult to spray with thermal spray, ceramic, for example, to coat these complex parts where it's a very poor line of sight. And the PEO as a technology offers you this unique opportunity to coat highly complex part with minimal line of sight. On this right-hand side, this is a job done by my colleague, Graham, who's done this wonderful job. This is drill slots about 1 millimeter in diameter and about 5.5 millimeter in length. As you can see, there's tiny, tiny bores being coated with the electrolytic process. And this section here, you can see further down the SEM picture, extremely high dense coating, even inside these tiny, tiny bores. Imagine that. It's a 1 millimeter width bore is 6 millimeter deep. The capability of the electrolytic process that you usually wouldn't be able to do with other coating technologies. So it does have a unique strong points. The another area is the additive layer manufacturing. Usually very fashionable now, additive manufacturing in particular, because it has got almost zero wastage, very little wastage. But the problem here is this is the job we did for space missions, and you can see this is like a flakes on the top layer. You don't want any particle generated on space missions, neither for other applications. The close-up picture, the SEM picture of this region shows these spherical unmelted Ti64 particles and lots of dust, if you like. So on the right-hand picture, you see those coated after PEO. These flakes are gone. It's absolutely gone. And if you see those closer view of this area again, those loose particles and those fine dust have disappeared. So what is happening here is literally, if you see those, while having those plasmic and volcanic eruptions, you are either cleaning those loose particles, you're dislocating those particles, and and they go into the electrolyte system, or you are melting and refusing and coalescing together. And that's exactly what is happening on those additive manufacturing parts. Another strong point is the continuous large and very small structures. And historically, Caronite as a technology, we always aimed for mid-sized components, about 1 dm squared to 10 dm square max, or sort of most of the parts. But we had some requests from space companies. Hey guys, we cannot use other coating technologies because the environment is we need a very, very good coating like PEO, but we need to coat 3 to 5 meter diameter for the next generation telescopes. Can you coat it? So we thought that, okay, this might be an opportunity. We wrote a small proposal to Innovate UK, and the UK Space Agency funded this project last year, very successful. This is a mock-up of a large disk. This is just a 24-inch diameter aluminum disk, for example. You can see those. So the beauty here is the whole part is not immersed in the electrolyte as you would do in normal PEO systems. This is only a segment is being coated. You can see that. You can see those plasmic events at the bottom here happening here, there. So only a small segment is being coated and continuously rotated as the Millennium Wheel. And the result here is, you can see this one here, a fully coated wheel. And we extensively analyze in terms of optical reflectance, adhesion, and other characterization technique we used. And the coating, in fact, is very similar to one we would have otherwise coated using a standard dipping process. Again, we talk about these little components again. Probably other technology would very much struggle. These are very, very tiny parts for surgical instruments, or this pick-and-place nozzles, very, very small. And this electrolytic process means you can coat extremely small or extremely large components. The next one we thought about, okay, why not use this technology also on tin foils? Of course, anodizing has been done for many, many years. The kitchen foils, so they're probably anodized, very thin coating, a few nanometers, but now we're talking about a thick engineering coating. So what we did here is we coated this 50 to 70 microns thick foil, rolled into about tens of meters, and we coated this in a continuous mode. And the idea is, rather having to coat a component, we coat this, for example, with a black coating, chop it off with the scissors, and then we stick on a laminable, flexible film. That's what exactly we did. We cut it, and we wrapped it around those cylindrical surfaces to make it black. And for example, this you can see, this example, if you can see, you can flick this black coating. This is under tension, and it's not coming off. So you can literally wrap it around a part, right? So it is still highly flexible. And finally, another final strong point is the repairability. This job was done for one of the space missions. What we did here is we coated a plate. We scratched these 3 long scratches with a diamond tool, and we masked 50% on the left with a tape and a paint, and then we recoated those damages. On the right, what you can see is a forced healing, I call it as, in the electrolytic bath. You cannot see those even seam here. It's almost like seamless. You can't. On this one, you can see a little bit like a scar tissue, like you on a human skin. You can see that. But when we measure the properties, they are identical to the original. The bond was extremely good. The adhesion was good. The reflectance was good, and the cross-sectionally also it looked very good. So what is happening here is I call as the preferential current flow. So you all need is to repair these components, high-value components, rather than stripping of the entire component. You coat locally where the damage has occurred, and it works in the principle of least resistive path. To summarize, PEO characteristics, it has got strong adhesion because it is a conversion technique rather than a deposition technique. It has got a very good fatigue performance. It has got much less fatigue debit than hard anodizing. It's a clean technology, very, very strain tolerant, highly strain tolerant, and importantly, is an inert ceramic and hence chemically very stable. Gives very high electrical insulation because it's an aluminum oxide, ceramic, in the case of aluminium. Extreme hardness because it's a corundum you can create on aluminium, and subsequent extremely wear resistance. And the most important thing is the process versatility. You can coat highly complex shapes. For example, this one, you can coat a tiny titanium bolt just on the surface, only the top landing only you can coat, right? You can see those, for example, a space baffle here, you can see those coated, even those tiny, tiny pinholes, if you can see here, coated, that needs to have very low optical reflectance. And you can also locally mask it very easily where you need these mask zones for electrical grounding purposes. And finally, if I see those samples here, this is your aluminium, a bare, humble aluminium. And that's what happens when you convert into a ceramic with the Caronite process. It's literally a corundum, an alpha alumina, extremely durable. You can cut glass with this one, and that's what it does. So having said that, the final video is it's an absolute last slide I would like to show you. This video was taken probably about 10 or 12 years ago, and this is the Caronite in production. You can see those about 25 to 30 frying pans being lifted on the flight bar, and is in an automatic fashion. It's moved from one bath to another bath, and you can see there's also plasma event happening on those parts. And I would like to thank you. I've taken 43 complete minutes. I hope you enjoyed the talk, and I hope you remember some of these videos and the PEO words, and I hope you'll come back to us and say, hey guys, maybe we'd like to do some PEO on light metals. And I want to thank you all for your patience and for your attention. Thank you so much.
Thank you very much, Suman, for that fantastic presentation. So what we're going to do right now is we'll move over to our sponsor spot for this part of the webinar. So I first have a short video to show from Optimal Instruments, and then we will welcome on stage Gregor Patzer from Optimal to talk a bit about the company and what they do. So I'll just turn off the screen share for now. You can stay on stage, Suman, if you like. If you just
I'm on stage.
if you could just if you just mute for now, just because we'll have some,
Sure. How do I
videos playing
do that?
and so on. So just the little microphone button in the bottom control panel.
So I need to go to the main Demi website, right?
It's okay. I can do it. There's just a little turn microphone off. Ah, there we go. Perfect. Excellent. So we'll put the video on.
Thank you very much.
Welcome. Sorry.
Yes, thank you for welcoming me, Sam.
Sorry, I was just about to welcome you to the stage. I'll bring up your slides now, and then I'll mute myself so you can give your presentation.
And thank you for the great presentation, Suman. As you saw in our video, some applications are quite similar to the field of our research and applications, and therefore I'm quite happy to introduce some buzzwords of what we are doing with our tribo testers at Optimal. So Optimal Instruments has more than 50 years of tribology experience in the field of application near tribo testing. I saw in your poll questions that many of you are working on mechanical testers and tribometers, and this is where we are at home for more than 50 years right now. We are placed in Munich, Germany. Today is almost a view like on this picture. Very nice weather over here. We are a team of more than 15 engineers with different backgrounds from chemical engineering, mechanical engineering, physical engineering, and our expertise and our mission is to bring tribological problems from the real field, from the real life into the lab, to simulate the problems on mechanical testers or tribometers with transferable results. And this is just some snapshots of the solutions, how they look like then later on the tribometer and on the test rigs. So you can see it's a really versatile testing platform that we offer at Optimal Instruments. So why does it make sense to use tribological test benches compared to field tests or rig tests? Most of you are already aware of those topics. Of course, the field tests have the highest practical relevance, but they take a long time. They are comparably expensive. And in most cases, they only deliver spot data and not exact data at dedicated operating conditions or so. The rig test itself brings a little bit more detailed data, has a good practical relevance, but nevertheless, the duration is still long, and in most cases, the expenses of running a bench test are relatively high. For example, 1 week of bench testing on a combustion engine costs about 50 to 100,000 euros. And that costs a lot. Imagine you have a fail in your test. That's kind of a huge loss of money in that case. The benefit of the lab scale testing compared to those field and rig tests is you have a short duration, you have relatively low expenses for one test, and you have a wide flexibility of parameters with a good practical relevance if you don't do only model test. So the trick in this case is you have always to try to bring the real stress collective into the tribo tester. And this is our expertise at Optimal. And then at the end, you can use the precise data out of the test bench for further data processing and the simulations and so on. And with that, close the loop to the real field to improve the products. Let me show you our main products with one example for one case study for each product. Unfortunately, Suman and I didn't discuss earlier, otherwise I could have shown exactly fitting use cases to Suman's application, but I think you will be able to imagine that we have similar test procedures also for applications as Suman presented. So one of our the smallest test trick that we have is the so-called ETS, Easy Tribology Screener, with online wear measurement. It's a simple and easy benchtop tribometer where you can do simple model tests under fretting conditions with adjustable temperatures, adjustable loads, adjustable sliding speeds, like we did in this case for our organic coatings. Those organic coatings are very thin films. In this case that we had, the target was to coat contact lenses with those organic coatings in terms of producing sustainable contact lenses that you can use several times with a high durability and with very smooth friction properties in order not to get any problems between the eye itself and the contact lens. And therefore we had 4 candidates for organic coatings. All were applied on bronze discs, and the counterpiece was a POM, a plastic ball, and we ran under dry and wet condition with the lubricant water. And you can see here, I just put some microscopic images after the test. One, the so-called, let's call it purple coating, had a relatively high wear under dry conditions and a very low wear under wet conditions. But interestingly, if you look at the wear tracks, even if there is a relatively higher amount of wear under dry condition, the wear track is very smooth. And this is what is relevant in the contact between the eye and the lens, that the surfaces always remain very smooth. Otherwise, you will have irritations. While this yellow disc, for example, produced in both cases, wet and dry, damages on the surfaces, the wear tracks look relatively destroyed and damaged, and this already disqualifies those coatings for the target application. If you compare the friction and the wear with online measurement, you see that the COF under wet conditions is nicely low. In this application, the wear is represented in the blue curves, and the friction is represented in red. And you also see that the repeatability is quite nice, even if this is an exotic application. while under dry condition, obviously, friction is higher and wear is higher. And this is how you can easily rank different coatings, different materials, different lubricants in terms of wear resistancy and friction behavior in a model test. Now let's switch to the next size of test bench, the SRV, one of the most famous tribo testers in the world, with lots of standard methods at ISO, ASTM, DIN, and so further, with different temperature options, low from -45 up to 1000 centigrade, with air conditioning system, different measurement possibilities for electrical contact resistance, acoustic emissions, and so on. One case study I would like shortly to show is the topic of gear components. This is kind of an overlay with Suman. So when you when you develop the new components of aluminum alloys with Suman's coating, you can test them on the SRV in terms of scuffing properties, where we have a very simple screening test. We increase the load stepwise and observe if and when, at which load stage, we detect scuffing failure, seizure, cold welding, whatever damages that are occurring in the gear. Another up-to-date problem is the out of the electric drivetrain, where we can test easily the compatibility of hairpin wires with EDF, the electric drivetrain fluid. Using the electrical resistance measurement, we can detect if there is a breakthrough of the layer, if there are damages, even after a longer time of test, and we can observe if the friction remains stable. And another very interesting application that we have today is hydrogen. You know that in many different applications, one talks about hydrogen to replace normal conventional fuels. And this is where we are developing now a hydrogen test cell, where we can do tribo tests under hydrogen atmosphere up to 100 bar. Last but not least, I would like to mention with one short slide our 2-disc test trick for slip rolling testing. This is more targeting on fatigue properties. There you can do heavy-duty traction tests with adjustable slip rates, high loads up to 5 kilonewton, with plenty of measurement possibilities. As you can see here in this short case study, targeting on friction and fatigue of coatings and alloys under slip rolling conditions, where you can nicely differentiate, on the one hand side, the friction properties, and on the other hand side, fatigue damages on the surfaces, where you can see pittings, micro pittings, and of course during the running in period you see also abrasion and all other mechanisms. And this is where I'm at the end of my presentation. I took a little bit longer than 5 minutes, but I hope it was interesting. And thank you again for joining the webinar today, and to Surface Ventures for hosting us, and to Suman for the very interesting presentation.
Thank you very much, Gregor. Great presentation. Always good to have an overview of some of the ways you may test some of these things. So we've got a few questions. So I'll proceed with the first asked question, and we'll go through the list like that. We just had a question from Sankara, so we'll take that as the last one so that we don't overrun too long. Before I begin, I just want to direct everyone towards the handouts tab. So if you're interested in any of the pieces of equipment that Gregor just talked about, you can find the handouts pertaining to those right there. So let me go right.
Thank you, Gregor. It was a very nice presentation. I've downloaded those brochures as well. I'm sure we will have use of that. Very good. Thank you.
Thank you.
Great. So we got our first question from Sankara here. It says, in reference to slide 15, the chromic conversion coating underneath the powder coating is thin, but has the ability to offer good corrosion protection. The PEO coating is porous. How could it offer a higher corrosion resistance?
Okay.
Suman, I can bring up slide 15 if that would be of
you let
use.
me do that. Shall I do that? Or?
It's okay. I can bring. It's okay. I can bring up.
You can bring up. Okay.
So right here. Yes. Let me just advance through these. Sorry. Please go ahead.
Right. Okay. Thanks, Sankara. Thanks for your questions. Very interesting questions. What it's doing there, actually, you just passed the slide, Sam.
Sorry. Did I?
Yes, that is one.
There we go.
So what is happening there? Just to respond to Sankara's question is, you have got the PEO layer on the aluminum substrate, which is atomically bonded layer, thin layer, it's got a very good bond. But then you have got lots of those pore architecture at the PEO. So what this PEO is doing here there is a bond layer for the powder coat or paint or subsequent layer. So it is extremely well bonded to the PEO layer. So you have got the extremely well bonded PEO to the substrate and extremely well bonded top layer to the PEO. And because PEO is electrochemically is an inert layer, you don't have the galvanic interactions between the alumina and the aluminum substrate. So what is effectively happening is on the damaged zone, you are expecting the corrosion to happen as normally you'd expect. It corrodes, but A, it is not driven badly by the galvanic interactions because there is no other cathodic couples. And B, it is because the corrosion is not pushing downwards. It just stopping there. Because the bond, the ceramic layer is stopping for further propagation, the corrosion creep. You don't have that in other phosphate treatment, other things, is because usually you tend to push those corrosion product underneath. And because the bond being not very strong, it tends to migrate underneath and gradually pushes up those polymeric layer, resulting in blisters and further propagations and peeling off the polymer layer. So that's exactly is happening there. So I don't know whether I've answered, Sankara, for your questions. You're happy with the answer, or?
I think that's clear to me. It seems like effectively two levels of protection that it is giving in effect. But let's move on to the next question. So we have Oleg, who has asked, you mentioned that the PEO layer is less brittle and it has a lower Young's modulus than alumina. What are the particular features in its composition, crystalline, and microstructure that leads to this effect?
Well, it is primarily given by the fact the PEO coating goes number of those discharging events, micro cracks and pores, very, very discrete pores and micro cracks. So just imagine that you have got those, it has got a crystalline matrix and some sort of amorphous phases within those cracks as well. So it's giving like a cobble effect, if you like. It gives you allow to flex. It's not a solid monolithic single piece ceramic that if you put stresses, it just cracks. That is what is giving you the flexibility. And that's why this is also this picture I'm going to show you again. This is a 20 microns coating. I'm literally bending it, right? So this allows you to, otherwise, if you have the monolithic ceramic coat, it will flake off. On the tensions is very good. If you do, of course, repetitive on the compressions and tension things, you will bound to damage at some point, but it has got a much, much greater strain tolerance. So did I answer, Alec, to your question, I hope? So
I believe so. Let's Oleg has just said thank you. There you go. We have our next question from Pavel, who has said, Cambridge Nanolithic is specialized in novel applications of advanced PEO. What is your view on PEO applications for vehicle electrification?
Thank you, Pavel. Very interesting questions. And I think PEO in general, we have this great opportunity. It's probably the right time. You're probably aware of that, what one of the guys in the Russian Aluminum Handbook said. We have passed through these Stone Age, we've passed through the Bronze Age, we've passed through the what's called the Iron Age, and this is the age of aluminium. Because we can do so much with aluminium. It's manufacturing technology. We have got printing technologies, the additive manufacturing with our little wasters. You can do so much about it. And this electrolytic process like PEO, and this have great potentials to offer in a variety of applications, and including the electrifications, vehicle electrifications, definitely.
Okay, great, thank you. So I have another question from Sankara, was asked, in reference to slide 30, it is not necessary all of the unmelted / partially melted particles present on the additively manufactured component should be removed during PEO. Moreover, PEO treatment again makes the surface rougher. Will it affect the fatigue property of the additively manufactured component? This is particularly important for implants.
Very good question again. As I said to you before, yes, PEO coating will generate some roughness and it will reduce the fatigue, but not to that extent to the hard anodized coating. But if you are already reducing the fatigue, for example, 80-90% with those large cracks and porosities in the additive manufacturing component, if you're filling those holes with PEO, you're coalescing, you're minimizing those cracks, I thought it's bound to get improvement, not the reductions. Of course, you cannot benefit 100%. You can go to the zero. Maybe you have to use other technology. Maybe you have to machine it first. Maybe remove those loose particles first by electrochemical cleaning or polishing technique. But what is showing there is the PEO process on its own. It can clean the surface. It can polish the surface. It can create those uniform coating to have a uniform coverage. So it's bound to improve the fatigue performance, additive manufacturing, definitely not reduce.
Okay, thank you very much. Let's move on to the next question here. Again from Sankara in reference to slide 24. However, I think you answered this later in the text.
I did, yeah.
Was saying, how was the non-exhaust emission measured? So I'll take note of this and pass on contact details.
Yes.
Of Sankara in order to get Fabian in touch with them.
Fabian will be very pleased, I think. Yes. I think, yes. Thank you.
Okay, excellent. Thank you. Another question from Sankara, who says, you've tested the friction behavior of contact lenses. So this one would be one for Gregor, actually, I believe. You've tested the friction behavior of contact lenses using water as a lubricant. Eye drops contain salt. Have you evaluated the friction behavior of contact lenses using eye drops or artificial tears?
Yes, of course. This was a larger study for the coating maker. I'm not allowed to share all the results, but of course we used a salt solution for the tests, the medical salt solution as well, and saw the differences. That's clear.
Okay, thanks, Gregor. I'm just coming to our final two questions here. The penultimate one from Hamid, who has said, hi, Suman, what is the edge of knowledge in PEO today? Are all of the problems solved?
This I like this question. And I think we are just exploring, the potential of this technology. There's an enormous potential, but but we are just unfolding the potential of this technology, and that's why I said to you before to respond to Pavel as well. We are on the age of aluminium. Aluminium is a lightweight, recyclable, is a sustainable material, and all these things. And because this technology is improving, I think we've got to see this. We are just unfolding our capabilities, I think, and you guys will be doing probably a lot more research. We as a team around the world. And if you see, I did have present today a Boolean search. Over the last 20 years, the growth of research in PEO has almost grown substantially compared to any other technologies. You can find today hundreds of publications every year on the PEO technology, because there's a lot of interest in this technology. Of course, we cannot solve every problem, but I'm sure globally, if we put all the efforts and do a lot more research, I think we can unfold many other attractive applications using this technology.
Okay, great answer. Thanks, Suman. Just as we come into the final question, I'd just like to point out to all of the audience that if you're interested in an attendance certificate for the event today, the link for that is down in the bottom left of the screen currently. So please do click on this if you would like an attendance certificate. They will not be available after this event, so please get it now if you are interested. Okay, and now we have our final question from QZ. I hope I pronounced that correctly, who has said, thank you for this great presentation, Suman. Regarding the friction of PEO in space, could you please explain why the coefficient of friction decreases from 0.1 to 0.04 when the pressure decreases?
Okay, I've got a very good answer for that. The answer is I don't know. Because this is done by someone else. I'm not the expert in this area. I was donated the data. I'm sure we can find it out together, Guji, but thank you for the question. Sometimes I don't want to answer the question is because that gives option to explore these questions even further to find the more better answers. So I apologize for that. I don't have the answer today, but I'm sure we can find it out for that, and I'll be in touch with you.
Okay, great. So with that, let's draw the webinar to a close. So just like to say thank you once again, Suman, for the fantastic presentation.
Thank you, Sam.
Always a pleasure to hear you speak. Thank you very much to both yourself and to Gregor for answering the questions today. Thank you to the audience for being with us and for staying. I know we ran a little bit over our normal time, but I absolutely think it was worth it. Great questions and great answers. So thank you all for that. I'd just like to say thank you very much to Optimal Instruments for supporting this webinar. As you see on screen, please do visit our website for recordings of all of our previous webinars. And soon we will be advertising our next webinar on the website as well. This will be held on the 30th of March. More details to follow, so please do go ahead and sign up to our mailing list for this. You can stay tuned for that. You can also find out information on our LinkedIn page. And also, we have our fortnightly newsletter, Modern Surface. If you sign up to our mailing list, you will receive this. And finally, I would just like to say thank you all for your support for this event. So please do let any of your colleagues, friends, anyone who think would be interested in this know. Be great to continue to grow our audience and reach more people. So with that, I'd like to say thank you all very much, and we will end the webinar there. Thank you all.
Thank you, Sam, and thank you, Rico. Thank you all. Thank you very much. Bye-bye.
Thank you. Bye.
Thanks. Goodbye, all.